40% of the entire universe just disappeared. Not dark matter, not some theoretical particle. Regular matter, the stuff you're made of. The atoms in your body, the air you breathe, the ground beneath your feet. Billions upon billions of tons of it, gone. And nobody knew where. For 20 years, astronomers have been dealing with the most embarrassing problem in modern science. They know, with absolute certainty, exactly how much normal matter the Big Bang created. The math is perfect. The equations don't lie. But when they actually counted everything in the observable universe, stars, galaxies, planets, gas clouds, everything they could detect with the most powerful telescopes ever built, they came up 40% short. 40%. Imagine if you went to the bank and the teller told you that 40% of all the money in the world just vanished overnight. No explanation, no trace, just gone. That's what happened to the universe's matter budget. The scientific community was baffled. Theories were proposed, arguments broke out, careers were built trying to solve this mystery. Because if we can't even find the normal stuff, the matter we're supposed to understand, how can we claim to know anything about the cosmos? But recently, everything changed. Scientists finally found it, and when you hear where it's been hiding this whole time, you're going to lose your mind, because it's been right in front of us all along. Let's back up for a second and talk about what we're actually dealing with here. When cosmologists talk about the universe, they break it down into three main ingredients. Think of it like a cosmic recipe. 70%, that's dark energy, the mysterious force that's literally ripping the universe apart, making it expand faster and faster every second. We don't know what it is, we just know it's there. 25%? Dark matter, invisible, undetectable except through gravity. It's the scaffolding that holds galaxies together, but we've never directly observed a single particle of it. And the remaining 5%? That's ordinary matter, baryonic matter, protons, neutrons, electrons, the stuff that makes up literally everything you've ever seen, touched, or experienced. You, me, planets, stars, your coffee mug, all of it. Now, 5% sounds tiny, right? But here's the thing, we should be really good at finding it. Unlike dark matter and dark energy, ordinary matter actually interacts with light. Stars produce light, planets reflect it, gas clouds absorb it. We have telescopes that can detect every single wavelength of electromagnetic radiation: infrared, visible, ultraviolet, X-rays, gamma rays, radio waves. We've got it all covered. Finding ordinary matter should be easy mode. Computer simulations gave scientists their first big clue. When researchers modeled how matter should behave after the Big Bang, something beautiful emerged. The universe wasn't just a random soup of galaxies scattered through space. Instead, it organized itself into an intricate structure that astronomers call the cosmic web. Imagine the largest spider web you've ever seen. Now scale it up to the size of the entire observable universe. The thick parts of the web, where the strands intersect, those are galaxy clusters, massive collections of thousands of galaxies bound together by gravity, containing unimaginable amounts of matter and energy. The thin strands connecting them? Those are filaments, cosmic highways stretching across hundreds of millions of light years, linking one galaxy cluster to another. And between all those strands? Voids, enormous bubbles of near emptiness where almost nothing exists. Dark, lonely expanses of space where you might travel for hundreds of millions of light years and encounter maybe a dozen galaxies. This structure isn't random. It's the direct result of how gravity shaped the universe over billions of years. Right after the Big Bang, matter was distributed almost uniformly throughout space. Almost. There were tiny fluctuations, regions that were just slightly denser than average, and regions that were slightly less dense. Those tiny differences matter a lot. Denser regions had stronger gravity, so they pulled in more matter from their surroundings. This made them even denser, which gave them even stronger gravity, which pulled in even more matter. It was a cosmic snowball effect. Meanwhile, less dense regions lost matter to their denser neighbors, becoming emptier and emptier. Over billions of years, this created the web-like structure we see today. But here's the crucial part. The simulations predicted that those filaments, those cosmic strands connecting galaxy clusters, weren't empty space.
They should contain gas, lots of it. But not just any gas. This stuff should be incredibly hot, millions of degrees, and incredibly diffuse, spread so thin that it's almost invisible. Scientists called it the warm, hot intergalactic medium, WHIM for short. And according to the models, the WHIM should account for most of the missing matter. The math checked out. The simulations were consistent. Everything pointed to the WHIM being the answer. There was just one tiny problem. Nobody could actually find it. Finding the WHIM turned out to be one of the hardest challenges in observational astronomy. Think about this for a second. You're trying to detect gas that's heated to millions of degrees, spread across distances of hundreds of millions of light years, with a density so low that there might be only 10 particles in a cubic meter of space. For comparison, the air you're breathing right now contains about 25 billion trillion particles per cubic meter. The WHIM is basically a ghost. It barely interacts with anything. At those temperatures and densities, individual atoms are so far apart they almost never collide. And without collisions, they can't radiate energy efficiently. They just sit there, superheated and invisible, floating in the darkness between galaxies. It's like trying to see your breath on a hot summer day. On a cold winter morning, you can see your breath clearly because the water vapor condenses into visible droplets. But in summer, the water vapor is still there. You're still breathing it out, but it's so warm and diffuse that it's completely invisible. The WHIM is that summer breath, except a million times harder to detect. For years, astronomers tried everything they could think of. They used X-ray telescopes to look for the faint glow of hot gas. They got hints, weak signals that could maybe, possibly be the WHIM, but nothing definitive. They used ultraviolet spectroscopy, looking at light from distant quasars to see if it was being absorbed by intervening gas. Again, hints, tantalizing clues, but no smoking gun. They tried stacking images, combining data from multiple observations to amplify weak signals. Better, but still not conclusive. It was like trying to solve a murder case where all you have are shadows and footprints. You know something happened, you know someone was there, but you can't catch them in the act. The missing matter remained missing. Scientists started wondering if maybe, just maybe, their models were wrong. Perhaps the WHIM didn't exist after all. Perhaps the missing matter was somewhere else entirely, in a form they hadn't even considered. Doubt crept in. But then, after 2 decades of searching, everything changed. The breakthrough came from an unexpected direction. Actually, 2 unexpected directions, using completely different techniques. The first came from a team of French astrophysicists who did something brilliant in its simplicity. They looked at old data with fresh eyes. For 20 years, X-ray observatories had been collecting data on the space between galaxies. Thousands of observations, 15,000 potential filament locations. But each individual observation was too weak to show anything definitive. The signal was buried in noise. But what if you combined them? All of them? It's like trying to hear a whisper in a crowded stadium. One whisper? Impossible. But 1,000 whispers coming from the same direction, all saying the same thing? Now you can hear the message. The French team used sophisticated statistical techniques to stack all that archival data. They analyzed the collective X-ray signature from 15,000 suspected filaments. And there it was, the WHIM, glowing faintly in X-rays, exactly where the simulations predicted it should be. Billions upon billions of tons of hot gas strung out along the cosmic web like dew on a spider's web at dawn. But the really mind-blowing confirmation came from a completely different approach. Fast radio bursts. FRBs are one of the most mysterious phenomena in astronomy. They're incredibly bright pulses of radio waves that last just a few milliseconds. They come from distant galaxies, and we still don't fully understand what causes them. But here's the clever part. FRBs are perfect for detecting the WHIM. When a fast radio burst travels through space, It passes through any matter in its path, including the invisible fog of the WHIM. This interaction does something measurable. It slows down the signal. Different wavelengths get slowed by different amounts. Longer wavelengths are affected more than shorter ones. This creates a time delay called dispersion. By precisely measuring this dispersion, astronomers can essentially weigh the fog. They can determine exactly how much matter the radio signal passed through on its journey from the source galaxy to Earth. A team at Caltech and Harvard analyzed dozens of these FRBs, ranging from relatively nearby sources to incredibly distant ones, billions of light-years away. The results were stunning. 76% of the universe's ordinary matter is floating out there in intergalactic space. Another 15% exists in halos surrounding galaxies. The rest is locked up in stars and cold gas within galaxies themselves. The numbers matched the predictions almost perfectly. After 20 years of searching, the mystery was solved. The missing matter wasn't missing at all. It had been there the entire time, woven into the fabric of the cosmic web, too hot and too diffuse to easily detect. But now, we found it. So why does this actually matter? Why should you care about some invisible fog floating between galaxies? Because this discovery fundamentally confirms our understanding of how the universe works. First, it validates the Big Bang theory. The predictions about how much matter should exist come from observations of the universe when it was only 380,000 years old. Finding that missing matter proves those ancient light signals weren't lying to us. Our cosmological models are correct. Second, it reveals how galaxies actually evolve. That gas in the cosmic web, it's not static. It's constantly cycling in and out of galaxies. When massive stars explode as supernovae, they blast gas out into intergalactic space. When supermassive black holes at the centers of galaxies erupt with energy, they push even more gas into the WHIM. This isn't random destruction, it's a regulatory system. If all the gas stayed in galaxies, star formation would happen too fast. Galaxies would burn through their fuel in a cosmic blink and go dark. But by cycling gas in and out, this feedback mechanism controls the pace of galaxy evolution. It's the universe's thermostat, and we just figured out how it works. The third, and this is huge, this discovery has given us a powerful new tool for exploring the cosmos. Fast radio bursts are now established as precision instruments for mapping the universe. Future telescope arrays will detect thousands of FRBs every year, allowing us to map the cosmic web in unprecedented detail. We'll be able to track how the web evolved over billions of years. We'll be able to test our models of dark energy. We might even be able to determine the mass of neutrinos, those ghostly particles that could hold the key to physics beyond our current understanding. For 2 decades, 40% of the universe was missing. Not hiding in black holes, not locked away in some distant corner of space, just invisible. Too hot, too thin, too spread out to see with the technology and techniques available at the time. But human curiosity doesn't quit. Scientists kept searching, kept innovating, kept pushing the boundaries of what's possible. And finally, they found it. The missing matter is in the cosmic web. It's in the glowing filaments connecting galaxies across hundreds of millions of light years. It's been there since the beginning, shaping how galaxies form and evolve, hidden in plain sight. The universe's inventory is now complete, and in solving this mystery, we've opened new doors to understanding the cosmos. The tools that found the missing matter, stacked X-ray observations and fast radio bursts, are now revealing secrets we never knew existed. The missing 40%? Found. And it's been connecting us all along.